In this section, we are going to learn about line integrals, and there's a couple different types. We're going to start off talking about scalar line integrals. Line integrals over a scalar function. Okay? And this is a pretty direct extension of the single variable integrals that we learned in Calculus 1. So in Calculus 1, you had some curve f of x, and if you integrated from a to b, it gave you the area under the curve between a and b, right? So that's the single variable case. Now, the multivariable case, we're going to extend this so we don't have to be so, so two-dimensional. But we're still going to want to find an area. So imagine I have some surface here. Okay, f of xy. All right, and somewhere below it in the xy plane, we have parameterized some curve. Okay, so there's some curve right here, which we could parameterize r of t, but let's just call it curve c for now. Okay, and the idea here is that we want to find, we kind of extend this up, we want to find the surface area of this, of the surface that results between curve C and the surface of our multivariate function. Okay, that's what we want. And we use this notation. We're going to integrate over the single, the scalar function f. We're going to integrate over C, and we use ds here. Okay, that's going to give us what we want. And I'll explain where that notation comes from in a moment. But before I do, let me give you a better picture of what we're dealing with. Always good to see it in a 3D calculator. Makes things a little easier to visualize. So I have here our surface, our multivariate function. And we can imagine below that we have some curve. Okay? The scalar line integral is going to integrate this function over the line, right? The scalar function over the line, scalar line integral. And so I get the area from beneath our multivariate function, beneath that surface, but above the line. Okay, so if I take out that, we're getting the area of that surface there. That's what we're looking for. Okay, so let's derive how we're going to find that. Now, when we looked at the single variable case, how do we do it? We broke it into rectangles, used a Riemann sum, right? And then took the limit as the number of rectangles went to infinity. Let's see if this color's a little better. Okay, so lots of little rectangles. Okay, we want to do something similar here. Okay, so I'm going to break this into little pieces. That are rectangular in how they're constructed. So I just need base times height of each one of these pieces. Okay. So if we look at just one of these rectangles, and rectangle may not be the right word, but they're a rectangle on the surface. The surface itself is flowing and curved. We're kind of taking a little rectangular chunk of it. If we were to make it straight, it'd be a rectangle, but it's curved. Okay. One rectangle, we want to find the area of the rectangle, which we know is going to be base times height. Okay. Now, to find the base, we're going to need to parameterize the curve. Okay, but not just any parameterization. If I use something like r of t, then I could say, well, if I'm going from here to here, going from maybe t0 to t1, then I could subtract them and find the length, right? Except it wouldn't be the length. It would be how much the time changes. If I have a parameterization that goes faster, then the difference between this time and this time would be smaller, right? If the parameterization goes real slow, the distance from this time to this time would be greater. So what I want is I want the difference between these to match the length of the base of each rectangle. Okay, so instead of having just any old parameterization, I want an arc length parameterization. Okay. Remember the arc length parameterization, the S corresponds to the length, the arc length of the curve from the start point to here. So the difference between two S's from S1 to S2 will give you the length of the curve between those values. Okay, so I'm going to need an arc length parameterization. In this case, the base is just the change in S's. Okay, and let me emphasize area of one rectangle. Okay, so the base is delta S, the change in the arc length of the curve going from the beginning of the rectangle to the end of the rectangle. And then I'm going to multiply it by its height. The height is going to be where the function value is along some point along that portion of the curve. Okay, so I pick some value S, I plug it in to my my parameterization of the curve, my arc length parameterization of the curve, and then I plug that into F, right? S star tells me how far along the curve I am. Okay, R of S star tells me the XY point at that location. And then if I plug it into F, that tells me what the actual function value is at that point, the height, going from here to here. Okay. So that is the area of one rectangle. Now I need to add up all the rectangles together to get an approximation of the surface area above curve C, but underneath the surface. Okay. So total area. Well, I want to add up everything from 1 to n. Let's say I have n rectangles. Okay. And I'm just going to swap the order here. So this one over here, this one over here. And I just want to make sure that my S star corresponds to my ith rectangle, right? Because for the first rectangle here, I'd use one height, but for, the second rectangle, I'd use a different S star because I need a different height, right? The third rectangle, I'd need a different S somewhere along this base here so that I plug it in, I get a different height. Okay, and the approximation is going to get better as n goes to infinity. So the bigger n is, the better the approximation. As n goes to infinity, the area itself gets better. So this is the answer we're looking for. Okay, it's just a really unpleasant way to express it. But what we can recognize here is that we have a Riemann sum. Okay, Riemann sum, we're taking the limit as n goes to infinity. And we have two things. We have some function, and then we have a delta s, and this goes to 0 as n goes to infinity. Because this is a Riemann sum, we can rewrite it as an integral. So it can be rewritten as an integral from the first s, which would be 0, right? Because where you're starting, you've covered 0 arc length, to L. Function becomes f of r of s, and the delta s becomes ds. Okay. Notice this kind of explains where this notation comes from. We're integrating over the curve. Okay, so they didn't find definite limits of integration like we have here. Okay, but they just left it c. They're integrating the function over that curve. Okay, the function, and with respect to the arc length. All right. Okay. So we essentially have our integral to find this scalar line integral, but to do it, we need an arc length parameterization for the curve. Arc length parameterizations, if you remember when we were dealing with arc length parameterizations, they're a great thing to think about in theory. They're very useful theoretically, but very unpleasant to work with in practice. So we use the theory to help us find the integral, but we don't actually want to have to find an arc length parameterization. So let's say we find some other parameterization. How would I rewrite this? So if I find some other parameterization, this would be a substitution. Okay. Now, in order to make a substitution to some other parameterization, I need a relationship with our arc length parameter s and some other parameter t. So remember, that if I have some other parameterization r of t, I could find the arc length parameter, the arc length function, using this formula. Okay, and this should be a review, but it may have been a while, so that's what it is. We're integrating the norm of the derivative of some parameterization. Here, the parameterization is with respect to variable t. Okay, so this would be the derivative of r of t, not r of s. Okay, in order to make this substitution work, I need to swap out my ds for my dt, so I'm going to take the derivative with respect to t. By the fundamental theorem of calculus, the derivative and integral, they kind of cancel and do each other, and I get the norm of r prime of t. Just the inside, and all I do is I plug that in. That's the fundamental theorem of calculus. Okay, which means I can make this substitution. I can swap out my old parameter, my arc length parameter s, for my new parameter t, so long as I swap out ds with r prime of t dt. Okay? So I'm swapping out my old parameter s and using some other parameter t. Hopefully a nicer parameterization for the curve, because generally arc length parameters are kind of gnarly. I can do that as long as I swap out ds with norm of r prime of t dt. And I'm going to integrate from the first value of t to the last value of t, whatever they are. Okay? So hopefully the process kind of made sense. But we found our formula. So whenever we're doing a scalar line integral, we can express it, we often express it as the integral over a curve C of some function f integrated over the arc length parameter. Okay? But to actually calculate this, we would find some parameterization for the curve C. Plug that into function f, multiply by the norm of the derivative, and integrate from the beginning of the curve to the end of the curve. Okay, so this is the formula that we will use to calculate a scalar line integral. Take a look at an example. Here we want to find the scalar line integral over curve C, where C is the curve parameterized by r of t equals ti plus 1 plus 2tj, where t ranges from 0 to 1. And we want to integrate the function y over 1 plus x squared, integrated over its arc length. Okay? So we know how to do this. The formula is we're going to integrate from 0 to 1. We're going to take our function, this function here, and we are going to plug in our parameterization, which helpfully in this case is already provided for us. And then we multiply by the norm of the derivative of that parameterization. And we'll integrate with respect to variable t. Okay? So the big thing we need to know here is what's r prime of t? Okay, so the first component, the I, derivative of t is 1, so I just get 1i. Plus, and then 1 plus 2tj, derivative of 1 plus 2t is just 2 times variable j. So that's r prime. Okay, so let's plug everything that we know in. So I want f of r of t. That means I'm going to plug r of t into my function. That means every time I see an x, I'm going to put in the first component, which is the t. Right? Remember, ti plus 1 plus tj is t comma 1 plus 2t. Right? So this is what I plug in every time I see an x in my function. And 1 plus 2t is what I plug in every time I see a y. Okay? So I'm going to plug in, I see a y up there, so that's 1 plus 2t over, and in the denominator, I get 1 plus x squared, so that'd be 1 plus t squared. Then I multiply by the norm of my derivative. So I have I plus 2j. So the first component is 1, so 1 squared, plus the second component squared, 2 squared, integrated with respect to t. All right? And that's the setup. Square root of 1 squared plus 2 squared, that's 5. So root 5, I could pull that out since it's just a constant. And I get 1 plus 2t over 1 plus t squared. And from this point, it's just a calculus 1 problem. So I won't go much further. I will point out that you could do a substitution here, right? Probably the best way to approach this problem is to do a substitution. Let u be 1 plus t squared. Derivative of u with respect to t would be 2t. And so it'd probably actually be best to break into pieces. Maybe I will do the whole thing. Okay. I'm going to break my fraction into 2. 1 over 1 plus t squared plus integral from 0 to 1 of 2t over 1 plus t squared. Okay, then I could do the u substitution on this integral. This integral, hopefully it's one you recognize. Integral of 1 over 1 plus t squared is arctangent of t. And for the second integral, I'm going to do my u substitution. 1 plus t squared becomes my u. And then 2t dt, that becomes my du. Let me make that clear. Multiply the 2t to, or the dt to the other side. 2t dt is du. And so I get 1 du. I've changed my variable of integration, so I need to change my limits accordingly. So when t is 0, u would be 1. And when t is 1, u would be 2. So I'm integrating from u equals 1 to u equals 2. And so the second integral, the antiderivative of 1 over u is natural log of the absolute value of u. I'm going to evaluate that from 1 to 2. So I get arctangent of 1 minus arctangent of 0 when I plug into that first, into this first term here. And let's plug in here, plus natural log of 2 minus natural log of 1. And if you're on top of your functions, you'll know arctangent of 1 is pi over 4. Arctangent of 0 is 0. Natural log of 2, there's not much I could do with that. It's natural log of 2. But natural log of 1 is 0. So I get root 5 times pi over 4 plus natural log of 2. Okay, that would be the surface area of the surface that would be above this curve but below this surface. So this is the function y over 1 plus x squared, and I want the surface area of the surface that I get when I look at the surface over this line, that's t comma 1 plus 2t, between that line and the surface. So that surface right there. And the area of that surface, that's exactly what we found here. Okay? That's scalar line integrals. Now let's look at vector line integrals. So for scalar line integrals, we integrated over a scalar multivariable function, right? The output of the function was a scalar. Here we're going to look at vector line integrals. Integrals over functions where the output is a vector. That is vector fields. We're going to integrate a vector field over a curve or a line. Okay? So imagine we have some vector field right here. The idea of a vector line integral, a good application. So imagine you have some particle and you want to move it along a certain path. Maybe something like this. Okay. Now, if you're moving the point along this path, imagine, so this vector field, it's like a force field. So it's acting on the particle, pushing the particle. Okay. Now, if we move the particle along this path, in some places, the vector field is going to help us, right? Like right here, the vector field is pushing the particle in the direction we want it to move, okay? In other places, the vector field is going to work against us, pushing the particle against the direction we want to move. And in other places, the vector field isn't really doing much to either push us in the direction we want to go or pushing us in the direction against the direction we want to go. It's not really helping us or hurting us. It's kind of orthogonal to our direction of motion. So what we want to do is we want to find the work done or the work required to move a particle along this path through this vector field. Okay? So to do that, what we want to do is we want to divide up the path into discrete segments. Okay? So maybe something like this. And we want to approximate how much work is required by the how much work is required to move the point along the path at for each segment. Okay? So let's look at the work required along one segment. Okay? And this will be an approximation, it won't be exact. So what we want to do is we want to estimate the amount of work done, right? The amount of help the vector field is giving us is pushing the particle, or the amount of how much it's working against us, right? So let's take a look at an example right around here. Okay, this is a good point to look at. Okay, the vector field is moving something like this, right? Now we could break this into pieces. We could look at how much actually maybe look at the next segment over. Let's look at this segment. Okay, we could break it into pieces. There's a certain portion of this vector here that is, let me make it a little bigger so it's a little easier to see. Okay, there's a certain portion of this vector that would be orthogonal to our path of motion, right? This portion here isn't helping us or hurting us. It's not pushing for us. It's also not pushing against us, right? But there's also a component of the vector that is pushing us in the direction we want to go. We want to know how much of the vector field at that point in this segment here is pushing us in the direction we want to go. So we'll take a point somewhere along the segment. And the idea here is we want to take our vector field at that point, at the point here, and we want to find out how much is of that vector field at that point is moving in the same direction as our path. In other words, how much of it is moving in this direction, tangent to our path. Now, if you remember, we could find the component of one vector onto another by taking the dot product, right? If I take the dot product of my vector field with the unit tangent vector, that's going to tell me how much of the vector field is at the point is pointing in the same direction of the unit tangent vector. That's going to tell me how much of the vector field is helping push me along. Okay, so I'm going to do it at the point, and then I'm going to multiply it by the length of the segment. So because we're multiplying by the length of the segment, because we want the length of the segment, we're again going to use an arc length parameterization. So we'll get an arc length parameterization. We'll plug in some value s, the s that corresponds to that particular point we picked. There's no perfect point here. I could pick this point or this point to be my representative point, but I picked this point. That's my representative point. I'm using that one point to estimate how much the vector field is acting along the particle along the whole segment. Okay, and then I take the dot product with the unit tangent vector at the same point. Okay, along the same, at the same value of s, okay? And then I multiply it by the length of the segment. So delta s, okay? So that's one segment. So if we want the work along the whole curve, we want to add up all of our approximations along the whole curve for every segment. So the total work required, we're going to add it up from 1 to n. We're assuming we are breaking our curve into n pieces. We're going to find the vector field along that segment, okay, the ith segment, and take the dot product with the unit tangent vector at that segment, the ith segment. And that'll tell us how much of the vector field is moving tangent to the curve, how much of the vector field is pushing with us, okay? And we have a delta s here. We take the limit as n goes to infinity, because the more segments we have, the better our approximation. So this can be the total work done, okay? Now we've seen this a few times now, so hopefully you're looking at this and you say, well, that's a Riemann sum. We have some function multiplied by delta s. We're adding them all up. We're taking the limit as n goes to infinity. So this is going to be equal to the integral from 0 to L of f of r of s dot t of s delta s, okay? Now, that's great. We have a way to find our work along this path as we pass through this force field, but it uses an arc length parameterization. We don't love that. If you notice, though, this is just like a scalar line integral at this point, right? We have a vector field, but then we take the dot product with a unit tangent vector. Once we do that, what do we get? The output of a dot product is a scalar. So together, both of this together is a scalar function. So looking at that way, this is a scalar line integral. Okay, once we get to this point, once we take the dot product, it's a scalar line integral. And we know from our previous work that we can rewrite this using some arbitrary smooth parameterization. As long as we multiply by the norm of the derivative of that parameterization. Okay? This is the formula we have for scalar line integrals, right? We just take our function, we plug in our parameterization, and we multiply by the norm of the derivative. Great. Okay? We can actually simplify this a little further, though, because that unit tangent vector, recall that the unit tangent vector is just the vector pointing, the unit vector tangent to the curve, right? So it's pointing in the same direction as r prime. Unit tangent vector is just r prime normalized. So if I plug that in, then you'll see that the norm of r prime is going to cancel. So we get the integral from a to b of f of r of t dotted with r prime of t dt. And that is the formula we're going to use to calculate a vector line integral. All right? So we got the formula, but the derivation of the formula, it implies a few, it's how we often notate these vector line integrals. So let me give you some notation. All right, so going back here, this is one way we sometimes notate a vector line integral. We take the integral over our curve C, of our vector field dotted with our unit tangent vector integrated over the arc length parameter s. Okay, so that's one notation. If we see that, we know we're dealing with a vector line integral. But there's another notation here. If we rewrite this a little ways, notice r prime of t is just the derivative of r with respect to t. And so writing it like this, we can imagine canceling out the dt's, can't we? And so thinking about it this way, it gives us the other notation that we often use. Integral over our curve of our vector field dotted with dr. Okay, both of these indicate a vector line integral of vector field f over curve c. Okay, and both of them, if we see them, we evaluate them this way. We find a smooth parameterization of our curve in the orientation we want it. We plug that parameterization into our vector field and then take the dot product of that with the derivative of our parameterization of our curve. Okay? Oh, and there's one other notation that we sometimes see with vector line integrals. So it stems from this here. Okay, so if we actually think about what vector field f is and what dr is, okay, vector field f, and I'm going to limit myself to 2 components, but it applies to 3 also. We could think of it as a vector of 2 functions, f and g, okay, and we could think of dr as a vector of differentials dx, dy. Okay, so if we have integral of f dot dr over curve c, we could rewrite this if we take the dot product as f dx plus g dy. Okay, and so sometimes we express a vector line integral in this way. It means the exact same thing. These two are the components of vector field f, and we are integrating over the curve. So let's take a look at an example here. We have a vector line integral. We're integrating our vector field f over curve c, where curve c is parameterized by t sine t cosine t. Okay? All right, so how are we going to do this? Well, we know from our work that we just did that in order to calculate this, we need a parameterization. We have that in this case. And we're going to integrate our vector field evaluated along this parametric curve. And we're going to take the dot product of it with its derivative integrated with respect to t. Okay? So that means I'm going to need the derivative of my parameterization, which in this case is 1 cosine t negative sine t. All right, so let's plug in. So we need f of r of t. So that means I'm going to be plugging in my parameterized curve, the x, y, and z components into the x, y, and z variables. Okay? So my vector field is negative 2z, 3y from negative 4x. So if I plug in, I get negative 2. The z component of my curve is cosine t, comma 3y. The y component of my curve is sine t. And negative 4x, where the x component of my curve is t. And I'm going to take the dot product of that with r prime of t, which I found right here. 1 cosine t negative sine t. Oh, and I am evaluating along the curve from 0 to pi. So those are my limits of integration. Okay. So let's take the dot product. Negative 2 cosine t times 1 is negative 2 cosine t. Sine t times cosine t. And negative 4t times negative sine t is plus 4t sine t dt. Okay? I'm not going to solve this all the way for you. But what you should do to solve this is break it into 3 pieces. So I have the integral of this term plus the integral of this term plus the integral of this term. Okay. This integral is very straightforward, right? Just take the antiderivative cosine t. With this integral, you'll need a substitution. Set u equal to sine t. The derivative of u is cosine t. Okay. This one's the one that's going to be a little trickier. The best way to approach this would be integration by parts. So let's kind of expand on this a little bit. So I won't solve the whole thing, but we will expand upon this integral, right? So remember, for integration by parts, we have integral of u dv equals uv minus integral v du. So I need a u and I need a dv in my original integral. The u I take the derivative of, the dv I integrate. Okay. So in this case, the u, I think t would be a good choice. And the reason why I'm choosing t is because the derivative of t is 1. That makes things nice and easy. Whereas the integral of sine t is negative cosine t. That really doesn't make anything better or worse because it's still just a trig function, right? So derivative of t, and I guess I should write dt here. Derivative of t is 1 dt, and the integral of sine t is negative cosine t. Okay, so if I were to plug in, I get 4 integral from 0 to pi t sine t dt is going to be equal to u times v, so u times v, so t times negative cosine t, minus integral v du. So v is negative cosine t, du is dt. And I'd evaluate all that from 0 to pi. Right? Now this integral is very straightforward. Right? So once you get that one, again, these other 2 integrals are straightforward and easy. So just that last one, we have to recall our integration by parts. But it's a fairly straightforward integration by parts problem. And so I'll leave you to do the rest. But finish this integral and then plug it in. Combine it with these other 2 integrals for your final answer. Let's take a look at just one more example of a vector line integral. This is using that alternate notation where we have dx, dy, and dz. So our vector field here will be the vector field with these 3 components. right? So x, y, z. That's the vector field over which I'm integrating. So I know that this line integral here, I can write it also as f dot dr, where this is the vector field we're dealing with. Okay, and what I want to do is I want to find a parameterization for the path over which we're integrating, the curve C over which we're integrating, and to evaluate the vector line integral, I find that parameterization, evaluate the vector field along that path, and then take the dot product with the derivative of the parameterization. All right. So what we need is a parameterization for our path. In this case, our path C is the line segment from 241 to 074. So it's just the line segment. Okay. And so my path, I need two things for a line. I need a point on the line, and I need a direction vector. So my point on the line, I'm going to take the first point, 241. And I need a direction vector. So since I want to start here and end here, I'm going to do end minus start. So this point minus that point, 0 minus 2 is -2. 7 minus 4 is 3. And 4 minus 1 is also 3. Okay, and we can see that if t is equal to 0, all this goes away and I'm at 241. I'm at the point I want to start with. I want to start at 0. And then when t is equal to 1, I have -2 plus -2, that'd be 0. I'd have 4 plus 1 times 3, that'd be 7. And 1 plus 1 times 3 is 4. So when t is 1, I end up at this point, 0, 7, 4. Okay? So this parameterization really does traverse the points from here to here when t is from 0 to 1. All right? So that's the parameterization I'm going to have. Let me rewrite it. So that's just all one vector. So it's 2 minus 2t, 4 plus 3t, 1 plus 3t. Okay? And then I'm going to need the derivative of that parameterization. I get -2, 3, 3. Okay, so let's plug in. Taking my integral, I'm going to evaluate my vector field, this vector field, over my parameterization. So every time I see an x, I plug this in. Every time I see a y, I plug in the y component of my parameterization. Every time I see a z in the vector field, I plug in my z component of my parameterization. Okay, so in this case, the vector field is just x comma y comma z. So I'll get 2 minus 2t, plug that in for the x, comma, and then for the y, plug in the y component, 4 plus 3t. And then for the z, plug in the z component, 1 plus 3t. And I'm going to take the dot product of that with our prime of t, which is right here, -2, 3, 3. Going to integrate with respect to t from t equals 0 to t equals 1. Okay, so I've set up the vector line integral. So if I take the dot product, first component times first component, I get -2 times 2 minus 2t. Second component times second component, I get 3 times 4 plus 3t. And third component times third component, I get 3 times 1 plus 3t. Okay. And you know what, I'll leave it there. It's pretty straightforward. From there, you just distribute, combine your like terms, and then power ruler 2, and you're done. Okay? Just one final word on the orientation of these curves. So for a scalar line integral, we are integrating a scalar function f over a curve C. And that's giving us the area of the surface that we get that's over the curve and under the surface described by the function we're integrating. Okay. Note that it doesn't matter which way we integrate, which way we traverse the curve. I could traverse it this way with this orientation, or I can go this way. Doesn't matter, because at the end of the day, I'm still going to be adding up all these little pieces, which give me the surface area of this shape. Okay, so it doesn't matter if I add up this one first and then this one and then this one, or if I start on the other side and add this one first and then this one and then this one, right? The orientation doesn't matter for scalar line integrals. So if I integrate the other direction, I get the exact same answer. This notation here means we're dealing with the same curve, but with the opposite orientation. Okay? Doesn't matter which way I'm going, whether I want to parameterize the curve so I traverse it this way, or if I parameterize the curve so I traverse it this way. I'd end up with the same answer because I'm integrating the same thing. I'm calculating the area over the curve and under the surface F. Okay? But for a vector line integral, it's a little different. So for a vector line integral, we're computing the work done by a vector field on a particle that moves through the field. Okay. Notice that if I have one orientation, I'm going this way. In some places, the vector field helps me. In some places, it fights against the motion of the particle, right? Some places like here, pushing the particle along, but over here, it's pushing against the motion of the particle, right? But what happens if we traverse the curve in the opposite direction? We traverse the curve in this direction. Now, every part of the vector field that was pushing the particle along is now pushing against it. Every vector that was pushing against it is now pushing for it. These vectors here, now it's pushing with the direction of the particle, right? And these vectors over here, now they're pushing against the motion of the particle. Because of that, if we change the orientation of the curve for a vector line integral, then we end up with a negative result, because every push here is a pull here. Okay, so we get exactly the opposite result. So to summarize, for scalar line integrals, the orientation of the curve does not matter. I could traverse it one way, I could reverse it the other way. Okay, for a vector line integral, the orientation definitely does matter. Okay, and so traversing it one way would be the opposite of traversing it the other way, would be the negative of traversing it the other way. Kind of like how I'm driving down a freeway. You drive down the freeway in the direction you're supposed to be going in, it's nice and easy. Okay, the traffic's pushing with you. If you go down the freeway in the direction you're not supposed to be going in, the traffic is pushing against you, it gets a lot harder.